So you want to develop a global IoT product. Yes, your new design is going to take the world by storm. But not so fast there, partner. Did you know that 85% of the world lacks terrestrial cellular coverage? So if your next design is truly going to be a global game changer, we should talk about NTN, the missing communication link for truly global IoT. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Paul Fadlovich from TE Connectivity and Martin Lesund from Nordic Semiconductor and I explore the what, why, and how of NTN technology. We also explore the role that antennas play in satellite communication systems, and how Nordic Semiconductor's NRF 9151 system in package and TE Connectivity's broad range of antenna solutions can jumpstart your next global IoT design. And before we get started, don't forget to click that link. There you can find even more information about this topic. Hi, Paul. Thank you so much for joining me.
Hi, Amelia. Thanks for inviting me today. I'm looking forward to it.
Absolutely. And hi, Martin. Thank you for joining me.
Thank you very much, Amelia, for inviting me. I'm very excited for today.
Excellent. Okay, so Martin, we are talking about global coverage with NTN today. But first, what exactly is NTN?
So NTN is non-terrestrial networks. It's basically communication over satellites. But in this context, we are talking about narrowband IoT over satellites. So NB-IoT over satellites. That is NTN in this context. And today's problem with cellular IoT is that 85% of the globe lacks terrestrial cellular coverage. And the solution for this is actually 3GPP NTN. So this standard comes from 3GPP, and this extends the standardized NB-IoT technology to satellite networks. And the 3GPP part is crucial. This isn't a collection of any proprietary satellite technologies and solutions. This is an official global standard, meaning that NTN is an integrated part of the cellular ecosystem. So imagine your device is tracking a shipping container. It can use standard LTM or NB-IoT network while it's at the port, but as soon as the ship leaves the terrestrial signal, that fades, and the device can then seamlessly roam onto the NTN satellite network. So the core network integration means that the data flows through the same pipeline to your cloud, using the same SIM and the same subscription plan. This eliminates the massive complexity and the cost of integrating a separate satellite modem, creating a single elegant solution for a true global connectivity.
So, Martin, there are two main categories here, right? GEO and LEO. Is that correct?
Yeah, so basically you have the selection between low Earth orbit satellites and geostationary satellites for cellular IoT applications. So especially for geo satellites, they are very high in orbit, but they appear fixed in the sky. So you have one single satellite covering a lot of the globe. The thing with the geo is that they're around 36,000 kilometers from the globe, but it allows for a more real-time connection where the satellites acts like a giant mirror, because the device sends their data to the satellite and the satellite mirrors down the data to the ground station, it's called. This works great for critical messages like SOS, or if you are in the middle of the ocean or in the woods where you need help, you can transmit through a geo satellite where you need to have confirmation and guarantee the delivery of the message is transferred quickly. However, because of the large distance, this means that the link is challenging and the data rates are low. And also your device has to be on air longer, meaning that the modem needs to be on for a longer period of time to actually send and receive the data. So that means you will consume more power when you are transmitting with the GEO. However, if you have a use case where you don't really send messages that often, which is typical for these critical alarms and SOS, then this is very doable on batteries. And the other satellite constellation is low Earth orbit, and these are much closer to the Earth. It's around 500 to 700 kilometers across the sky. So this means you need a lot more satellites to cover the same area as a GEO satellite will. So one single LEO satellite will, for example, have one orbit around 90 to 100 minutes, meaning it will go around the world. So if you send a message to satellite and the time it takes to kind of go around the world, it would be around 90 to 100 minutes. But since it's so much closer to the Earth, this makes the radio link much easier, allowing for a much higher data rate. But most importantly, you have a much shorter on-time air on your device, meaning that the modem only has to be on for a short period of time, which is fantastic for IoT devices that need to have extended battery life. Initially now, LEO networks use store and forward model because they haven't got that many satellites in orbit. So this means that they will store the message and the data of what your device has sent to it until it delivers it to a ground station on Earth. So it means you can have a high latency today. And like I said, the time it takes for a LEO satellite to go one orbit is around 100 minutes. This means you can, in worst cases, have over 1 hour of latency of your data going from the device to your cloud, for example. But this doesn't matter for many applications, so it's ideal for applications where you need to report data where immediate response isn't critical. So this can be agriculture, sensors, smart metering, it can be smart city, etc. These are very suitable using LEO, as this has a very low battery usage.
So, Martin, talk to me about the use cases for this kind of technology. This could open up a lot of different markets across the world, right?
Yeah, exactly. This is been the missing link in cellular IoT. The major struggle with this technology, with just regular LTM and NB-IoT and Cat1bis, for example, is that if you don't have coverage, you cannot talk to your devices. And now with NTN, you really can have true global connectivity wherever you are. So it's a game changer. It's a buzzword used very much, but in this case, it's really true. For example, in logistics and asset tracking, you can now finally have a device that tracks a container from a factory in Asia across the Pacific and then on a truck through North America without ever losing its connection, meaning you can track the location and the condition of this asset. And in agriculture, you can, for example, deploy sensors across thousands of acres to monitor soil moisture or, for example, track the location and the health of your livestock, all without worrying about any cell coverage. So in the middle of America where you don't have cell coverage, there could be places there, or especially for Australia, we see use cases where people are struggling with the cell coverage. So NTN will enable these places to share their data to the cloud. But especially also for safety and in maritime on the ocean, this is truly a game changer for smaller vessels that can't afford traditional satellite systems that can be expensive. Now they have a affordable tracking and safety system they can use with NTN. And last but not least, utilities and infrastructure. You can now have a smart meter or a monitoring system on infrastructures in the most remote locations. It can be on oil stations out in the ocean, or like you see in this picture here, these windmills that usually are placed in hard to reach places. So this means you can bring efficiency and safety to the entire grid. And I really think that NTN is the missing link for all of these new applications. But I think the most exciting part here is that the new use cases that we haven't really thought about yet. So I'm really excited to see which this technology can unlock for the users.
So, what kind of solution from Nordic Semiconductor would you suggest using for these kinds of designs?
So from Nordic side, to build a global product, you need a solution that's flexible and power efficient and of course easy to use. And from us, that solution is the NRF 9151 system in package module. This device supports LTM, NB-IoT, and now NB-NTN, so NB-IoT over satellites. But of course, it also supports GNSS. But the most important takeaway is you don't need a separate module for NTN. You can just use this one module, the exact same hardware that our customers are used to, or new customers that they use for terrestrial-only products, can now be configured with the NTN only, or kind of a hybrid mode where you either use LTM or NB-IoT and switch to NTN whenever you need to. So, for example, like a fallback solution. So in the old days, a fallback solution could be that you used 4G and then had to go back to 2G to have connection. But now in 2025 and in the future, you can use NTN as this fallback. So this also dramatically simplifies design, the supply chain, and the product management for your end product, because you only need to care about this one chip. And what's a key thing with this module that we have made is that everything inside here is developed and designed by Nordic. It's our own chipset, it's our own design, so we have full control of all its features and fixes, etc. for our customers. And also the main thing with our kind of solution here is that we have separated the modem and application processor, and the application processor is open, so you can run everything on this device. We have delivered SDK, so they can write the code and put that on the device. You don't need an external host, but if you want to, you can also use an external host. And we have designed the 9151 to support the critical S-bands and the L-bands frequency that's used by NTN providers. So that ensures that you have a future-proof platform. And of course, it's built on the Nordic DNA to be ultra-low power, which is absolutely essential when your radio link is hundreds of kilometers away. So if you want to have long battery life, our solution is great for that. But yeah, the last thing I want to say is that our entire ecosystem from our nRF Connect SDK and our world-class development tools is that to help our customers go quickly to market with their cellular IoT products and then now NTN products fast to market.
So for NTN, the antenna is a critical element to consider, right?
Yeah, exactly. So this is something we have seen some customers think about too late in their projects. They think that the antenna is something they can just slap onto the design and it should work. But it's actually a critical link. And now when you're actually talking to satellites far, far away compared to a base station, you really need to consider your antenna design crucially. So even if you have the most power efficient module, that's only the half of the equation. You need to have a good antenna design to ensure that all your data is transferred on a good link. And the performance of the antenna is critical here, because if it's not, this will force the modem to work much harder to increase its power output, and then also use more repetitions, etc. That will, of course, drain your battery. So it can actually be a single point of failure of the design. So choosing the right antenna and integrating it correctly is fundamental for a product success in the cellular IoT world. And especially now with the non-terrestrial network, the antenna is key. And that's also very good that we have T connectivity today to talk more about the antenna part.
Okay, so let's bring in Paul now and talk more about the role that antennas play here.
Thanks, Martin and Amelia. For satellite communication, the antennas have to perform, better than for standard terrestrial networks, right? This is due to the significant loss we have in signal strength during the transmission. As Martin mentioned, LEO satellites can be like 500 to 700 kilometers or further away than normal terrestrial networks. And that distance has a significant impact on signal loss. And you can kind of see that in the formula to the top left of my slide here, right? The other factor in signal propagation loss is frequency. Emerging satellite networks are typically operating in the L band, which is around 1500 megahertz, and the S band, which is around 2 gigahertz. But terrestrial networks, those typically have also operated at lower frequencies. They'd have some bands down in the 700 to 960 megahertz range. And those lower frequencies, which have longer wavelengths, would provide much better propagation characteristics. So now we have these satellite NTN devices that are operating at much greater ranges, with greater propagation loss due to that distance, as well as the loss due to the frequencies used. And now, my prior slide, that showed a very basic use case, right? An agriculture monitoring device in wide open space. Yeah, unfortunately, the reality is just never so simple. Even in rural environments, there's hills and mountains, and dense foliage and clouds and other things that just impact that line of sight. And then other applications like logistics tracking, there might be device shadowing by other structures within the port area or on ocean cargo freighters, for instance, very dense environments there, and even in less dense environments like rural, right, or construction or mining sites, you might still have obstructions shadowing the line of the site, not only to the terrestrial networks, but even low Earth angle satellites that are up in the sky. So, satellite NTN, it's an emerging technology still. There's one well-known player that's got hundreds of satellites deployed. That situation means there's a higher likelihood of satellites overhead. But most of the players these days so far are newcomers that have fewer than a dozen satellites operating, and their networks are growing. But in the interim, the devices on the ground still may need to reach further across the sky to, at a lower angle to reach those fewer satellites. They need reassurance of a robust link so that when the satellites do pass overhead, the connection needs to be made, without risk of failure. As Martin mentioned, if it has to keep trying to connect, you could possibly drain your battery much more quickly.
So, when it comes to antennas, we need to keep efficiency and gain in mind, right?
Yep, for sure. A key use case for NB-IoT is a battery-operated device, again, with intermittent operation, as Martin said, right? And those devices need to ensure a reliable connection when the device is planning to transmit and receive the data. The device saves battery by not always being on. The antenna choice and design plays a big part in this. Antennas have two key parameters, right? Efficiency and gain, as you mentioned. Efficiency is the ability of the transceiver and the antenna combination to get that energy out of the device and into the airspace. And gain is more of a measure of how well the antenna focuses that energy in a specific direction. Battery-operated NB-IoT devices, they can conserve their power by using a more efficient antenna, as well as ensuring that antenna energy is pointed in the right direction, up in the sky, be it up in the sky towards that NTN device or across the horizon for dual mode devices, operating in terrestrial mode. So on the bottom of the page here, I try to show kind of on the left, a historical SATCOM antenna where it's a very high gain pointed directly up in the sky. And I showed two plots, right? One is kind of a three-dimensional plot, so people can really understand what I'm talking about. But traditionally on data sheets, a lot of times we'll show just an elevation cut for representing what we're talking about here today. And you can see that the energy, again, is pointed upward strictly for the SATCOM antenna. But for a terrestrial antenna, right, you want that antenna to point across the horizon. So we have more of what we call an omnidirectional antenna that's kind of got that donut shape, and all that energy is pushed towards the horizon or slightly up tilt a little bit to catch the cell towers that might be elevated up a little bit higher, right? But the new NTN plus TN devices, they kind of need to work in both modes, both environments, as Martin mentioned, right? So you need to have gain patterns that have both that broad coverage across the horizon as well as coverage up to the sky.
That makes sense. Now, what kind of antenna solutions does TE Connectivity offer to assist with these kinds of designs?
At TE, we have a very broad antenna offering for both terrestrial and non-terrestrial cellular networks. The terrestrial cellular networks typically are broadbanded in frequency, right? So they operate kind of from roughly 600 megahertz to around 3.5 or 4 gigahertz. The inclusion of the newer SATCOM non-terrestrial network applications, right, means the antennas also have to operate in the L band. Again, that's around 1500 megahertz, and the S band, which is around 2 gigahertz and above a little bit. So for the most demanding applications, customers tend to use external antennas for higher efficiency and better gain, especially if their device is in a metal cabinet or something that does not have good propagation. You can put those antennas up on a pole. And I show here some antennas and their elevation gain patterns. This represents the RF energy in a vertical plane, as mentioned on the previous page. Our OC baton antennas is a classic dipole. It's very broad banded, has good gain across the horizon. This one additionally offers some gain overhead to really support the NTN bands in that satellite environment. The L001257 is a monopole structure. What that means is that utilizes the metal surface that it's mounted on. And a good example is an IoT cabinet that might hold an IoT device. The impact of that metal surface, we call it a ground plane, is to direct the RF energy upward, which is actually a benefit for SATCOM applications. And then we also offer low profile puck style antennas. Again, good gain patterns. And by being low profile, they tend to be a little more tamper proof than some of the higher antennas. But again, you might have some trade-offs in performance because of the low profile nature. And then you'll also see on my slides here a little bit of an asterisk sometime on the L-band products, right? And the reason here is that these traditional cellular networks didn't really operate in those bands, or we didn't always emphasize their operation on the data sheets. So we're in the process of kind of upgrading our data sheets now, and you'll soon see much more pronounced characteristics of these antennas in the L band. They're operating there well now, but we just haven't really had the chance yet with this fast-moving technology to get the data sheets updated. On the embedded side, we have high-in-demand peel and stick flexible printed circuit antennas. They're kind of a good compromise of cost and performance. What happens is a customer will stick these to the sidewall of their non-metallic device. They may have a plastic or fiberglass box out in a remote environment. And so by adhering that antenna kind of up off the circuit board surface, they're able to get better propagation. And these really provide a good, reasonable performance, with a reasonable cost. And then we also have wide-banded surface mount antennas, right, that cover the cellular bands, including the L band and the S band. Surface mount antennas are a little bit harder to design in. You got to match the circuitry a little bit. We have good FAEs available to support the customer's design-in efforts. But once those are designed in, manufacturability is much easier because those surface mount antennas are literally just a pick and place on the customer's board. So from a performance perspective, though, the gain patterns tend to be a little bit more inconsistent for surface mount antennas, right? So not only in the 360 degrees around the horizon, but across the frequency bands as well. So I tried to show it in the lower right-hand graph here on this page, where I show 2 or 3 different frequencies, and those frequencies have a little bit different gain patterns you can see. And that's just a natural complication, if you will, of developing broadbanded surface mount antennas. So, and then I just want to have a little fair warning here that, what I'm showing here is just a couple of bands for each product. And so, make sure you check our data sheets for the exact performance to see if it's going to fit your use case.
For sure. Now, are there any other ways to determine what makes a good antenna for NTN?
Yeah. Like in terrestrial networks, there's kind of been a long-standing capability of professional antenna companies to support their customers with over-the-air testing. And DE can also do that now for NTN customers, right? This requires kind of a combination of both the antenna plus a radio module and having that radio module powered up. For NTN networks, the key parameter is reference signal received power. Although there isn't really a formal spec set yet, generally better than minus 120 dBm is kind of the ideal for these low data rate applications. RSIP can be affected by the antenna efficiency and gain pattern, as well as other environmental situations like the satellite elevation angle, atmospheric conditions, etc. And so what we did is we've tested a set of our catalog antennas for this S-band usage, right? And we've been able to achieve and validate that the RSRP levels are above that minus 120 dBm threshold. So we feel confident that, we can work with our customers and get performance that's going to be adequate in most cases. So, and we're going to continue to do our efforts and do more testing with L-band devices and continue to expand as the NTN networks evolve and develop, right? And continue to increase our capabilities for over-the-air testing in support of our customers. So it's an exciting time to be in telecommunications with so much change going on.
Absolutely. So before we go, what would you like my audience to take away from today's Chalk Talk?
From Nordic side, I think we need to come to the reality here that NTN actually can deliver true global IoT coverage. So it's the ultimate range extender for narrowband IoT technology. So directly talking to satellites to reach the rest of the 85% of the world that's not with terrestrial service today. And the second point is that we deliver a cellular module, 9151, that provides you with everything you need from terrestrial connection and also satellite, having everything running on the device. And We actually launched a development kit in December 2025, NRF9151 SMA development kit with SMA connectors, so you can test whatever antenna you like and check the TI connectivity antennas and test the performance with that, for example.
Yeah, and for the TE connectivity side, we've learned that battery life is greatly affected by the use of the right antennas. Look for the right combination of antenna efficiency and gain, where it's being directed to make sure that it's going to meet your applications, and that will help reduce the overall power demand of the device. And then as far as the offering, TE offers a very broad portfolio of antennas that can meet the, emerging direct-to-device applications.
Fantastic. Well, I think that's all I have time for today. Thank you so much for joining me, Paul.
You're welcome. Really appreciate being here today, Amelia.
And thank you for joining me, Martin.
Thanks, Amelia. It was great.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.